And thanks for joining, everybody. My name is Clayton Barrows. I'm a researcher and group manager here at the National Renewable Energy Lab in GPAC, and I'm going to talk about the Sienna modeling tools that we've been developing over the last 7 years here at NREL. So the power systems are changing. There are new sets of resources coming online. Those resources expose new opportunities to create a more sustainable grid, but they also create new challenges. So many of the resources coming online are variable. They have new sources of uncertainty associated with operating them, and there's many more of them in many cases. At the same time, electricity demand is changing. We're seeing a significant load growth because of electrification. We're also seeing many more controllable loads coming online. And these also create new opportunities and a need for new tools to be able to understand how to maintain reliability under these changing conditions. Reliability and resilience has become even more paramount under this new framework of, or this new paradigm of significantly more controllable assets and the uncertainty that all the assets face. Here in GPAC, we've been at the forefront of these transitions in the past. We've led the charge on understanding how to maintain reliability under these sort of transformations over the last 20 years, starting with the Western Wind and Solar Integration Study. About 20 years ago, we started to understand what were the grid changes needed to be able to accommodate about 20% wind and solar. And we learned that it wasn't very much in that case. But with more modern studies or more recent studies with renewable energy futures or renewable electricity futures, LA 100, the North American Renewable Integration Study, and the ongoing National Transmission Planning Study, we're learning that the grid changes required to accommodate higher shares of renewable energy and maintain reliability are more transformational. And we need new tools to be able to understand how those grid changes will occur and how to manage them properly. In particular, a study that some of my colleagues did a few years ago framed this reliability problem in terms of the 4 fundamental requirements of maintaining reliability in power systems. And they framed it such that there were these capabilities. So a power system needs enough capacity to meet load at all times. And it needs the resources, it needs enough flexibility in the resources to be able to manage the uncertainty in the forecast errors, uncertain responses, and balance the system at all times and be able to shift power or shift generation to meet load at all times. It also needs the capability to maintain a steady frequency by controlling those assets and the response of those assets to different outages or perturbations on the system. And finally, it needs the ability to be able to inject real and reactive power and maintain a steady voltage so that electricity can be transmitted around the network safely and reliably. The challenge with these 4 pillars is not so much the complexity of them themselves, which they are complex, but it's that to plan for those and maintaining those over the future power systems requires making planning decisions across 15 orders of magnitude in time. Starting with an AC cycle, which is about 60 hertz, what is 60 hertz here in the US or 50 in other places, we have we have to manage timescales that deal with the automated response of many devices. So we need to make sure that the devices that are automatically going to respond to different conditions are going to do so in a reliable fashion. We also have to understand how to plan and deploy new assets in the planning context, and that often takes many years or decades. And in the middle, we have a scheduling timescale. So we need to be able to schedule on a minute-to-minute, hour-to-hour, day-to-day, or season-to-season basis the assets that we do have so that we can maintain supply and demand balance and reliable operating conditions. When we think about this in terms of modeling and simulating future systems, we can think about it in really three timescales. Starting with the planning timescale, where we're trying to answer questions about when, where, what should get built. And then moving down in time a little bit, we think about the scheduling timescale. Okay, once we have a representation of what might get built, how do we schedule that to maintain reliability? And how do we manage the forecast errors that those assets might face and make sure that under any particular condition, we have enough assets to reliably operate the system? And then finally, how do all those plans and schedules respond to the different conditions that they might encounter and in a reliable and stable way? Can we demonstrate that they're going to respond in a reliable and stable way? And so this is really the response time scale. We've simulated these timescales, and we do simulate these timescales in our integration studies regularly. And there are a number of ways that we typically start those integration studies by assembling the data that informs them. So we look at the wind, water, solar, the system data, as well as the transportation choices, the end use load choices, and think about how does that go into how infrastructure is actually built. So starting with distributed adoption models, we think about how are people going to decide whether to build wind and solar on their roof, or solar on their roof, or make distributed generation adoption choices, which is often not a system-wide economic decision. And then we also take into account the different end-use decisions on electricity demands and forecast the load growth potential over many years under different scenarios. And all of that goes into a capacity expansion model like REEDS, which was highlighted in the last Powered By webinar, where REEDS will make the system-wide economically optimal choice to decide what gets built when and where. And under these adoption decisions, we start to frame and develop scenarios. And then we move into a refinement stage where we're running production cost models and reliability models and stability models to show that these future grids can operate reliably and stable. And there are several operational decisions that can be refined in there too, in terms of how is a system scheduled? What reserve margins do you run with? What are the control strategies that you do to make sure that things are operational? But by and large, we're trying to figure out how do we operate a fixed set of infrastructure in a reliable fashion going forward, and in some cases provide feedback to say this scenario is not a good one, or this scenario, or these are the trends that we think are most valuable. This study process is really complex and historically has relied on a set of distinct models across all of these different boxes. And that each time each model feeds into the inputs of the next model, and those transitions are incredibly challenging, not just because they're distinct models and they rely on distinct data, sometimes with different assumptions, but also because there's the data translations, and the humans that do the data translations are error prone. And so just the handoffs between this in this framework is an extremely large challenge in understanding how this energy transition might take place. This is one of the reasons we built Sienna. And Sienna is an open source ecosystem for power systems modeling, simulation, and optimization. And we set out to build a more coherent approach to addressing many of the modeling modeling activities in a workflow like I just showed. Sienna is really made up of several capabilities, starting with Sienna data, where we have a coherent set of a coherent data model for multiple different modeling applications and for power system analysis. We can hold data for modeling activities that include dynamics, scheduling, and planning, and enable fast access to a coherent set of power system data. Sienna Ops is really targeted at the modeling power system scheduling. And so we have a number of capabilities that address the modeling challenges in the scheduling timescale. And then Sienna Dyne is a dynamic simulation capability where we can understand the system response, the dynamic system response under different conditions. We've been using Sienna on a number of different DOE-funded activities, including the Water Power Technologies Office HydroWires program. We're using Sienna to build the largest scale production cost model ever assembled with the National Transmission Planning Study and simulate the grid operations under a variety of different future transmission network. We explored the reliability and resilience of Puerto Rico's energy future with the PR100 study, and then we've been exploring some new approaches with the GMLC, and I'll highlight some examples from each of these in a few minutes under the different capabilities. We also see a lot of value in using Sienna in places where transparency and agility and economic cost effectiveness is very important when making grid modeling choices. And so we have seen a lot of value in the RELAC program, where we're exploring the energy transition in several Latin American countries, and we can very quickly assemble models to address different grid studies, or just to explore power system data in different places with the Sienna tools. I'll step into sharing a little bit of the details about the different capabilities now. So like I said, Sienna data is really focused on coherent and efficient access to power systems data. And we have a number of capabilities that include reading standard data formats and exploring large-scale data sets with lots of time series data and accessing it to enable downstream modeling capabilities. One of the primary benefits that we've seen with Sienna data is that we have been able to scale our impact by just creating a reproducible data management framework. So when we do a grid planning study, we are taking in data from a number of different sources. We start with typically a network model in like a load flow case, like a PSSE file. We add on things like generator characteristics like costs and emissions. We layer on regional load time series, hydropower availability, renewable energy, sometimes electric vehicle information, and a number of other things. And each of those things is generated from a different process and doesn't always align with the power systems data. And so we have a number of utilities in Sienna data to programmatically create those matchings. They align the units so that we're talking about consistent measures of capability, and then correct the data and make sure that we are making a coherent representation of the system, and check and make sure things are working well. Once we have done that with Sienna data, we come up with a complete data set, and we call that a system in Sienna. And that system can be the starting point for many of the modeling activities within Sienna, but it also can just be a place where you can do power system analytics. You can explore the connectivity of a network. You can understand the capacity versus the load at different periods. You can do a number of different just simple data analytics, which is very valuable. And then in many cases, we have seen, because clients have requested it, or because there are capabilities in commercial tools, that we need to export that data and format that data so that it is usable in other modeling softwares. And so we have a number of capabilities for exporting the data into other formats. And so all of this is done in a way that it is programmatic, and so it's reproducible. So say you get a new load flow case or a new cost representation, you can replace just that piece, rerun the whole thing, and you have a new data set. And this has been immensely valuable, and has avoided some of the errors that we've encountered in the past, where we've had to correct costly mistakes that we've encountered. Additionally, we've seen Sienna data enable rapid explorations of new capabilities. So I was recently asked to develop some new capabilities around calculating interregional transfer capability. And I was able, because Sienna data existed and because I had fast access to large scale system data, I was able to, in a matter of hours, stand up a prototype for calculating interregional transfer capability that I could then test on the entire eastern interconnection. And then once I had a good understanding of how things should work, I was able to develop this lightweight graphical user interface to allow other people to use it that maybe weren't comfortable with using a command line interface. The next capability is Sienna Ops, which is really focused on the simulation of scheduling processes, including the sequential simulation of scheduling. So we do optimal power flow, unit commitment, economic dispatch, but not just those problems. We also enable production cost modeling by feeding the results of one scheduling problem into the inputs of the next, so we can enable large-scale simulations over long periods of time. One example of how we've used Sienna Ops was for the Puerto Rico 100 project, where just like some of our other grid studies, we had a sequential modeling process where we gather the data, explore scenarios, and explore how the Puerto Rican grid might evolve under those different scenarios, and then evaluate the impacts and ensure reliability in task 4, and then several reports and visualizations, all with a theme of lots of stakeholder input and engagement throughout the whole process. Sienna Ops was really focused on this intersection between the scenario generation and the impacts analysis. So we were both taking the results of a capacity expansion model and putting them into a production cost model, simulating that production cost model and resource adequacy model to ensure system reliability, to understand the different operational changes that might need to occur, and also giving feedback back to the capacity expansion model so that when we did find times when the system was not going to be reliable, they could amend the expansions and provide more assets to maintain reliability. And then we were able to give the results to downstream models for further stability and reliability analysis and economic impact analysis. So Sienna Ops provided a lot of benefit in the programmatic workflow that this project required across multiple national labs and the activities that we were doing. In addition to the programmatic advantages, we were able to rapidly develop some new scheduling practices. So we found that because of the small scale of the island and the lack of resource diversity on the island, that the system was having a lot of trouble under typical day-ahead and real-time scheduling operations to handle forecast errors and maintain some power supply through the night, because it wasn't forecasting cloudy conditions a day or two ahead of time, and it wasn't able to store enough energy in the batteries to maintain power supply. So very rapidly, we were able to develop a multi-day storage scheduling phase where we were able to look ahead a little bit further, estimate cloudy conditions, and conservatively store enough energy in the battery storage system that was projected on the system to maintain enough state of charge to be able to manage the forecast errors and maintain power balance throughout the year. And this flexibility of Sienna Ops allowed us to do this very quickly. Additionally, one other advantage that we had was because of the platform flexibility and our ability to deploy on the high performance computing and cloud architectures that we have access to, we were able to simulate the number of scenarios that the Puerto Rico project required very quickly. So we were able to just simply simulate the 84 simulations that we required for each annual representation of the system on parallel pieces of hardware and get the results in as quickly as 4 hours for any modeling iteration. And because we did so much feedback with the other modeling activities, we did this many times, and we used well over 1 million node hours on our high performance computer to execute this study. So that was very beneficial. At the end of the day, we were able to get some new insights as well on on transmission utilization and the needs of the system going forward. So one interesting result was that in the past, there's been a fairly robust high voltage 230 kV transmission network in Puerto Rico. That network has faced some challenges to the hurricanes, but it was designed to get the generation from the southern end of the island to the northern end of the island where the load is. Under the high solar futures that we were projecting for Puerto Rico, solar is developed around the outer edge of the island, often close to the load centers. And so the value of that 230 kV network is diminished. But at the same time, because the solar is distributed, it's close to load, but not next to load. And we need to significantly enhance the 38 kV line, the 38 kV network that exists on the island, which is also experiencing a large amount of destruction after the hurricanes. And so we were able to identify that with the flexibility of Sienna ops to be able to represent transmission in different ways. Another application of Sienna ops was on the GMLC Flex Power project, where we explored hybrid system operations and bidding practices. We explored new ways of scheduling hybrid resources with wind, solar, and storage to manage forecast errors and develop optimal bidding strategies for the hybrid resources. Then with Sienna Ops, we were able to demonstrate the reliability and economic benefit of the bidding strategies by custom extensions, or with the custom extensions that we made to Sienna Ops very quickly. And because of the scalability of the tools that we were depending on, we were able to do that at large scale, and we wouldn't have been able to do that if we had just started from scratch and written a scheduling problem in our own custom way. Finally, I'll talk about Sienna Dyne. So Sienna Dyne is a full dynamic simulation capability that we have written in Sienna. And we built Sienna Dyne because we recognized that with the transition to wind and solar and battery resources, there's a new set of opportunities that are presented by these inverter connected resources. Inverter-based controls happen at a time scale that's a little bit in the middle. So historically, we've had a lot of electromechanical and thermodynamic phenomena and some electromagnetic phenomena on the electric system that we need to understand very well. We've also had some lightning propagation that happened very fast. But these inverter-based controls kind of sit somewhere in the middle, where sometimes they are representing, or sometimes they're at the wave phenomena scale, and sometimes they're at the electromechanic and electromagnetic scale. And so because there are so many of these devices being integrated, and they have these new control opportunities, and they're fast, that we see some needs for some new modeling capabilities. And really the issue is that there are a set of existing scalable modeling tools that have served the industry very well, but they're designed to represent the slower timescales associated with electromechanics. And they're not designed to represent the faster timescales. The tools that are designed to represent the very fast timescales don't scale well. They're very complex and cumbersome to work with, and they create an extraordinary amount of data, which is difficult to manage and analyze. So we have this situation where the existing large-scale tools on the left, like PSSE, PSLF, the positive sequence tools, they scale very well to represent large numbers of devices on large-scale systems, but they aren't appropriate to represent the fast time scales. And historically, we've jumped all the way to the right to the waveform simulations to represent things like lightning propagation, but those are very complex, computationally complex, data complex, development complex tools that are challenging to work with. And we explored some newer approaches with the DQ0 models and found that they can be appropriate for representing many of the timescales associated with inverter controls, but can be also scaled to represent large number of devices efficiently. So we're finding some sweet spot and have developed Sienna Dyne to specifically represent these inverter controls. And we've seen an enormous amount of benefit. So relative to PSCAD, one of the waveform tools, we are able to simulate the timescales of inverter controls, we're able to run simulations about 100 times. Well, we're able to run simulations considerably faster. But when you consider model initialization and the data processing associated with actually end-to-end simulations and getting results, we see simulations of up to 100 times faster, and we can get equivalent results. And we've done an enormous amount of benchmarking to show that the Sienna Dyne capabilities can get equivalent results to PSCAD with large-scale simulations. Another benefit that we've seen extends beyond just the simulation framework. So what we really care about as researchers and system analysts and system engineers is accelerating the process of getting answers. And so there was a publication from Australia where there were some data around developing new control models for devices in PSCAD, and the cost associated with the engineering time to develop those control models is enormous. And so with an open source tool written in a scientific computing language that is easy to develop, we've seen a pretty enormous reduction in the development cost for exploring new modeling or dynamic control strategies in Sienna Dyne relative to PSCAD. And so we've seen about a 40 times reduction in development cost or development time because of the modularity associated with the way that we have designed the Sienna Dyne tools. And that modularity also benefits us in the simulation approach because we're able to apply different modeling numerical integration techniques and get results fairly quickly. And so why do we care? I think it ties back to the fact that in this energy transition, we are facing a number of challenges, one of which is this interconnection process, where the interconnection queue is extremely long and getting longer. And it's mired partially by the impacts, the need to maintain reliability, and the fact that the impact studies that are going to guarantee or ensure reliability that the system operators and planners need to conduct to maintain reliability can take very long. And if all goes well in US interconnection queue processes, we're looking at best 4.5 years of coordinated generation and transmission approvals. But it never really happens that way. There's a number of delays and things that happen. Many of those delays are associated with the system impact studies themselves. And so we are trying to use the tools like Sienna Dyne to automate the impact study because we have this programmatic interface, because we can scale to large pieces of hardware, and because we can do it all in a fairly computationally efficient and scalable approach. We believe that we can automate the impact study step and explore many, many more conditions in a more coordinated way to help address some of the interconnection queue process. So the process itself relies so heavily on simulations that if we continue to rely on the simulations that are most complex and most data intensive, we may never be able to scale those simulations to comprehensively evaluate interconnections and do so in a way that is more less incremental. Because in the past, this sequential process of saying adding one resource is going to lead to stable, so adding two resources can also be stable. Well, we understand that those two resources may interact in ways that create instabilities, and so we really do need to evaluate them in a more comprehensive way to evaluate groups of resources, and we need scalable tools to do that. And we believe that Sienna Dyne is a step towards making that possible. These types of applications are what we are exploring with Sienna Dyne. We have a number of others, and we have a very comprehensive set of capabilities. We've seen over 10,000 downloads across the open source Sienna tools, which are all written in Julia. And we've got a number of Julia packages that make up the capabilities that I've spoken about. and a large team of about 30 some contributors at this point across NREL, other national labs, and other institutions as well. So with that, I'm happy to take some questions, and I want to thank my team as well. None of this is a solo effort, so I want to be appreciative of everybody who has contributed to these, contributed and supported this effort. So, thanks.
Awesome. Thanks, Clayton. And thanks for all your questions. We already have quite a few in the chat or in the Q&A box. So just a reminder, if you have questions, drop them in that Q&A box at the bottom of your screen, and we'll be answering them live right now. I'm going to start reading some out to Clayton. So the first one we have is from back at the beginning of the slide deck, I think around slide 11. What do the color codes refer to on the slide for different timescales of operation planning and dynamics?
Nothing in particular. I think that mostly we had I had the color coded in terms of whether they were automated responses versus sort of planning, non-market planning decisions versus scheduling decisions, which are often settled in a market context. So, but I loose color coding at this point.
Great, thanks. Next question. Is Sienna using PSSE 34 or 35 version of .raw data?
So we have parsers for versions 33 and 34. Don't quote me. I always get time mixed up. So I believe it's 33 and 34, and we have I believe one of our team members has a prototype for parsing version 35 as well. So it's kind of evolving at the moment.
Great.
You're welcome to follow up on email on that, and we can get you I can get you a more accurate answer.
All right, next question. Could you expand more on any support for moving between or across timescales within the context of a single study?
Yeah. So I think that it is fundamentally challenging to move between planning and scheduling, and between scheduling and scheduling and response timescales, and thinking about those large groupings that I described earlier. We have addressed some of the challenges by simply holding the data in a coherent way, and so we can now hold a system data set that represents different expansion options and the systems that exist at different times, and the dynamic models associated with all of those assets within a single data set. So that's one aspect of the challenge. Additionally, another aspect of the challenge is that the modeling paradigms are quite different, especially between scheduling and dynamics, where you're moving from an optimization paradigm to a dynamic system of differential equations paradigm. And so there's still an overlap of the initialization results are based on the scheduling decisions that are made. And so we have now modeling capabilities where we can populate the initialization of a dynamic simulation with the results of a load flow problem and things like that. There are still several areas that can be improved. Some of them are things like translating scheduling results that are obtained with linear approximation of power flow, so deep sea power flow assumption, translating those into an AC feasible power flow result, and getting both real and reactive power injection for a particular set point. Things like that are areas where there's additional need to refine the modeling capabilities, and we're actively developing many of them, and are trying and are finding that the Sienna framework makes that development fairly easy to plug into the framework where we can manage these large scale data sets and things like that. So thanks. That's a fun question that I like to talk about.
All right, next question. How would you describe your partnership structure outside of the US, such as in Latin America? How is the cost structure formulated?
So that's I think a question for our lab business development. It can take a few different forms, depending on the type of arrangement that fits. In principle, Sienna is a set of open source capabilities, so people are free to use them. People are free to make use of them. We can provide limited support through email and Slack channels, and are occasionally happy to meet with people. Much of that initial support is unfunded, so there's a limit to what we can provide. And so beyond that, there are partnership capabilities, and we do have some support capabilities for some partnerships through some of our international work programs. But if you're interested in more, or interested in exploring that more with us, please feel free to reach out via email.
All right, next question. Has Sienna been used on smaller scales, such as a campus or a military installation?
So we have seen some, so we are targeted at the transmission scale. And so with all of our tools, we have made the single line assumptions of balanced three-phase power flow in the network. And so to the extent that those assumptions are valid enough or hold, there's no reason it couldn't, beyond the reason that those assumptions might not be valid, there's no reason you couldn't apply it to a campus scale system. And I've seen some examples of that, and I've seen some municipal examples where people are making some planning decisions, and they're not as concerned about the electrical parameters and the electrical details of their system. So they think that it's okay to make those assumptions on even those small scale systems, and are finding value in the open source nature and the ability to explore lots of time series, for example. So there are some examples, but a lot of the work we've done has been in making sure we're representing those electrical details very well, and that's not necessarily valid on the small systems.
All right, next question. Can you say more about how Sienna can connect operation scale simulations with planning scale simulations? Is it just by using Sienna ops and using a longer unit of time in the simulations?
That is one way. Yeah, so we have some longer unit of time. We also have now some capabilities that's one step. Another approach is to represent the future infrastructure, that expanded infrastructure in a single system, and allow for models to evaluate the differences between one pathway and another. And then a third option is to actually, now we can store the hypothetical resources in a system, so that we can, and we don't have this yet, but so that we can explore the expansion options of those hypothetical resources. So there's a few different layers there, and the most well represented layer in the existing tools is the ability to explore the operations of different infrastructure in kind of a scenario-based approach.
All right, next question. Can you clarify if Sienna Ops gives the capabilities of both production cost models like Plexos, as well as probabilistic RA analysis capabilities like PRAS or SERVM in a single toolkit?
So At this moment, we have Sienna data. We have a tight connection between Sienna data and PRAS, and so I've in the Puerto Rico 100 study, we were actually using PRAS as the resource adequacy framework, but we start with a Sienna data set, and I think we're evolving towards a paradigm where that's the normal process. And I'm getting kicked out because of a fire alarm. So, don't know what to do. I guess we will follow up with the rest of the questions offline.
Okay.
I can try and join in on my phone as I walk out the door.
Yeah. Oh, bummer. Jacqueline, what do you want to do here?
If Clayton can keep answering orally, I mean, we don't need the video.
Okay, I'll call in my phone just a second.
All right. While he's doing that, I'll see if there are any that I can answer in here. We have tons of questions, so thank you, everyone. I will not be able to answer any technical questions about Sienna, but we'll see if there are any questions about the rest of the Powered by series.
This is Madeline. I think one of the questions Robert asks about trainings, and that is a good question. I think what we could do is on the Powered by Webinar series page, we could probably compile all of the trainings that we do have available for the tools that have been featured in the series. So I know of some that exist, but I think we'll just have to connect with some of the other researchers to make sure that we have all of them in one place. So that's a good question. We can do that.
Right. So yeah, that question was, does NREL offer trainings on the operations of the Sienna model or any other model provided in the Powered by series? Hey, Clayton. You making it out okay? Oh, you're on mute. Oh no. Now he's frozen.
Okay, can you hear me now?
Yes.
Okay. I'll walk away from the crowds of people and and continue to address questions. So yeah, where are we?
All right. Stay safe.
Oh, the PRAS and Servum question. So yeah, so we have production cost modeling capabilities similar to those of Plexus, and then we enable resource adequacy by having a very tight connection with PRAS and are leveraging that more and more, such that I expect that's going to be the regular way we do it sometime in the future.
Great. All right, next question. Does Sienna have methodologies to effectively design in redundancy into the grid system components?
We have some. So we have some. I mean, we can represent ancillary services and reserve requirements, and then we have some N-1 transmission network formulations that are in various stages of development. So we're working towards having more robust redundancy requirements represented, but we do have some of the standard ones.
All right. Next question. When you mentioned Sienna Dyne is able to run 100 times faster than PSCAD, what kind of detail are you considering in the model when doing this kind of benchmarking?
So that benchmark representation is with a relatively small system. I think it was a 5-bus system with a electromagnetic transient simulation, and then beyond that, I would have to refer you to I think it's in a publication, but I can follow up with the details of the actual inverter controls that are represented in that simulation.
All right. Next question is, can you give us an idea of how much calibration effort is required for utility ISO to use Sienna? Example, if we are trying to analyze RA across MISO or perhaps a large utility like Excel, Colorado.
So an example. So the typical way we've been exploring, so typically the sort of baseline data that informs a study like that comes from, usually we start with a PSSE load flow case. And the benefit of that is that it is somewhat consistent because it's already assembled in a modeling tool for the load flow condition. And then layering on top of that something like generator outages or different wind and solar availability, there is some sort of configuration requirement. It's not typically enormous, but for resource adequacy, it's really pretty straightforward depending on how much of the uncertainty you want to represent. If you want to represent many years of lots of wind and solar uncertainty and load uncertainty and transmission line outages and generator outages, it gets more and more complex by how much you add on. But for example, in the Puerto Rico 100 study, we were able to stand up a basic resource adequacy model in about a day. So in about 8 hours a day. So.
All right. Perfect. Next question is, how would you describe the accessibility of Sienna to new users? For example, what level of experience with modeling, program languages, etc. would a person need from ground zero? What amount of training materials exist? Which Madeline touched.
So we are under a sprint, a substantial effort to improve our training materials. So we've recognized that this has been a shortcoming in the past and are putting us a major effort over the summer to increase our documentation and our training materials, our tutorials and things like that. So that is they exist now, but they're set to improve substantially over the next several months. Then in terms of fundamental requirements or expectations of a user, the vast majority of the capabilities, aside from a few limited exceptions, the vast majority of the capabilities are command line based in the Julia modeling or in the Julia language. So some familiarity with scripting programming languages and like Python or MATLAB is very useful. I would not say that someone needs to be an expert programmer to use Sienna. We do not. Someone doesn't need to write a for loop, for example. We do see some value in having some familiarity with programming, though, and some comfort with writing commands in a terminal, because most of the interfaces that we've enabled are command line based. In terms of modeling familiarity, this is one thing that we're trying to address a bit with our documentation updates is we recognize that in the past, our documentation has very much written from the standpoint that the user has a fairly deep understanding of power systems modeling, and we're trying to generalize that a bit so that it's not quite so hard to approach, make it a little more approachable. So we're working on that, and we've recognized it's an area of improvement. So.
Great. All right, next question. Can this platform also help with modeling a green energy EV charger infrastructure?
Same comments about sort of distribution scale and municipal scale assumptions of a network exist. So there's still some challenge. We are making single line assumptions. So sometimes that's maybe not the most appropriate application. However, we do have some capabilities on representing EV charging preferences and EV charging implications on system impacts. And so there are some use cases where I think Sienna could be valuable in that context in understanding the impacts of the EV charging network deployment. But there's kind of a wide range of applications there, so I won't go any further on that.
All right. Next question is, what number of clusters are available as simulations?
I don't know. I don't, yeah, I can't say that I followed that question.
Okay. We'll leave that one. And if you want to follow up on that, whoever
Yeah,
asked that question.
Feel free to write an email. It sounds interesting, so I would like to answer, but I don't really know how to.
Perfect. All right. Next question. Is Sienna open source or just open user?
It is 100% open source. We have a BSD3. We have BSD3 licenses on all of our software packages, so we are completely open source.
Awesome. Next question. We have so many questions in here and just a few minutes left, so we'll try to get through as many as we can and answer any that we don't get to via email. But the next one is, any current or future plans to work with Clean Energy State Alliance regarding energy storage interconnections, challenges and solutions?
That sounds awesome. I would very much like that. And those are relationships that I am actively pursuing, similar ones, but I do not have that one currently on my list. So whoever wrote that, I would very much appreciate an email and to explore some options there.
Perfect. Yeah, and that was submitted anonymously, it looks like. So just go ahead and reach out via email. Clayton's email is on the screen here to follow up. All right, next question. Can Sienna support N-1 power flow modeling?
I mentioned this earlier. We do have some new capabilities where we have an N-1 formulation and are working to continually evaluate and improve the performance of that. And one of the challenges is what's the interface defining which contingencies to represent? Is it all of them? That tends to not be particularly scalable. And then how do you otherwise define them? So we are actively working on more representations, but we do have the kind of fundamentals in place.
Awesome. All right, next question. What scale can Sienna handle for instantaneous or snapshot DC power flow scenarios? Did I hear correctly earlier that you ran such a simulation for the entire Eastern interconnection?
Yeah, not just the entire Eastern interconnection. We've done a snapshot for a representation that includes all of North America. So it's 120,000 node simulation or something on that scale for a single snapshot DC power flow. We can do unit commitment and dispatch on roughly 75,000 node representation of the Eastern interconnection. And I don't think we've tried to do a full continental scale one yet for that. So large.
All right. Is there any reason for choosing Julia over other languages that are more spread, like Python?
Yeah, there are a couple reasons for Julia. One, Julia is touted as being a fast option similar to Python. That can be true if you are careful. That maybe factored a little bit into our decision. But more so, probably a bigger factor is that the optimization libraries in Julia are more advanced than those in Python, or certainly were when we started down this path several years ago. In general, I've been quite happy with the choice of Julia. It doesn't particularly limit us in terms of interaction with other tools, and so we have some efforts to make a wrapper, a Python interface for all the Sienna tools. Those aren't quite mature yet, but there's not really other than time and support, there's not really a barrier to making that happen. So I've been quite happy with the use of Julia.
Perfect. Okay, and there's a few more in here, but we'll have to answer those via email because we're running short on time here. So we'll connect with you after the webinar via email. Shout out to Clayton for answering everything from the fire drill. Are you still out there?
I figured I'd stay out here for a few minutes while I rather than reconnect to the internal internet. So I'm now, you can have a tour of the NREL campus here.
Perfect. Right.
Thanks everybody for joining. I really appreciate it and appreciate the questions.
Yeah, thank you for all the questions, and I'll just quickly run through. So our next webinar in the series is on the demand side toolkit, our DS toolkit, which enables detailed analysis of current patterns and future projections of end use loads. And that webinar will take place on July 9th at 10 a.m. Mountain Time, 12 p.m. Eastern, just like this one. And you can register for that on our Powered by Webinar Series webpage, which I am about to drop in the chat, the link to that. And thanks again for everyone who attended.